This video will focus on acid chlorides, including their preparation, naming, and reactions. Acid chlorides can be prepared from carboxylic acids using a reagent called thionyl chloride, or SOCl2. Now, we saw this reagent previously in Chapter 12. It was used to convert alcohols, or OH groups, into Cls. So it's the same type of conversion here, where we take an OH, treat it with the thionyl chloride, and the OH is converted to a chlorine. Now, the mechanism is slightly different than the mechanism in Chapter 12. However, you don't need to know the mechanism for this class. If you are curious, however, it is in the book. Since acid chlorides are derived from carboxylic acids, their names are derived from carboxylic acids as well. So for this example, we have 3-methyl butanoic acid. And what we're going to do is we're going to replace the IC with YL, and we're going to replace the acid with the word chloride. So we will end up with 3-methyl butanoyl chloride. And that will be the rule for all names of acid chlorides. You'll just replace the IC and acid with YL and chloride. For the carboxylic acids attached to cycloalkanes, so with this one we have cyclopentane, carboxylic acid, and with this we're going to replace the entire word carboxylic with the word carbonyl, and we'll replace acid with chloride. So we end up with cyclopentane, carbonyl, chloride. Acid chlorides are the most reactive of the carboxylic acid derivatives. And if you look towards the end of the chapter, you'll see that there are a bunch of different types of reactions that acid chlorides can undergo. Now, this figure may look a little intimidating because how are you supposed to memorize all of these different reactions? But what I've done is I've actually separated them into different categories. So first, we can focus on these two reactions here. Now, this blue square is going to focus on using water and alcohols as the nucleophiles. So we're really going to be focusing on oxygen-based nucleophiles in this type of mechanism. So on later slides, I'll go through an example of what this mechanism would look like. Next, we can group all of the nitrogen-containing molecules together. So all of these amines will use nitrogen as the nucleophile to attack the carbonyl. These two, we have lithium aluminum hydride, as well as a new reagent that we'll go over. These are going to use hydrogen as the nucleophile, and we'll see how those mechanisms are going to produce the two products shown here. And finally, we have Grignard reagents and a new reagent that looks like this. This type of reaction is going to use carbon as a nucleophile. And again, we'll look at the difference between the mechanisms in later slides. So now let's take a look at the reaction of acid chlorides with either alcohols or water. So I will start with this acid chloride, and I'm going to run this in a solution of ethanol. Now, in these types of reactions, pyridine is often added to the solution. Now, pyridine is a weak base, and pyridine is used to neutralize any HCl that can be formed. We'll see how this would be possible in just a bit. So in our first step of the mechanism, the oxygen of the ethanol is going to act as a nucleophile, and it's going to come over and attack the carbonyl carbon, kicking the electrons up onto oxygen. Now, as we saw in the first video, the next step is going to be to reform the carbonyl. So the electrons will come down, form our double bond, and kick off our chlorine, which is a good leaving group. Now we still have a positive charge on our oxygen that needs to be restored to neutral. So our next step is going to have a weak base come in and remove this extra H. So we can either have another ethanol molecule take the H and give the electrons to the oxygen, or sometimes chloride that was just kicked off can also act as the base to remove the H. So either one of these can happen, and that if you can imagine if the chlorine acts as the base, it will form the HCl. So that's why we need pyridine to neutralize it. Now ultimately, we will turn our acid chloride into an ester. Now, if water were used in this mechanism, we would turn the acid chloride into a carboxylic acid again. Now let's take a look at an acid chloride reacting with the amines. So we'll start with the same acid chloride. And in this case, we will use ammonia as our amine. Now, often we need excess ammonia or excess amine, or sometimes it's written as two equivalents. But we'll see why we need the excess amine in just a bit. So similar mechanism as with alcohols and water, the lone pair on the nitrogen are going to make the nitrogen act as a nucleophile. It will come over, attack the carbonyl carbon, kicking the electrons up onto oxygen. Now the nitrogen will have a positive charge. Our next step is going to be reforming the carbonyl and kicking off the chloride ion. So our last step is going to be removing the extra H from the nitrogen, and this is where the extra ammonia comes in. So ammonia is a stronger base than the chloride ion, so the chloride's not really going to be acting as the base in this case. The ammonia will come in, take the extra H, give the electrons to the nitrogen, and we have now converted our acid chloride into an amide. So this mechanism will be the same no matter what's attached to the nitrogen. So we can have either ammonia, a primary amine, or a secondary amine, and it will be the exact same mechanism. Now we'll take a look at acid chlorides reacting with LaH, or lithium aluminum hydride. Now we've already seen that LaH is capable of reducing a carboxylic acid down to a primary alcohol. So we'll see a similar type of mechanism with the acid chlorides. So with lithium aluminum hydride, we have an aluminum bound to 4 hydrogens. The aluminum has a negative charge that's stabilized by a positively charged lithium. Now, since aluminum is a metal, it does not like to have a negative charge, so it's going to want to get rid of a hydrogen as well as the electrons as fast as it can. So we're going to see the electrons between one of the hydrogen atoms come up to the carbonyl carbon and kick the electrons up onto oxygen. Now we're going to reform the carbonyl. The electrons will come down and form the double bond and kick off the chloride ion. Now we have an aldehyde. Now we saw in the previous chapter that aldehydes are also capable of being reduced with lithium aluminum hydride. So another molecule of LaH will come in and it will further reduce our aldehyde down to an alcohol. So as long as there's a carbonyl present, the reaction will keep going. Now at this point, we can't have the electrons come back down because there's nothing to kick off. Hydrogens are terrible leaving groups as well as alkyl groups. So the molecule will be stuck here until it's treated with a proton source such as water. Upon treatment with water, we will protonate that oxygen. And finally, we will create our primary alcohol product. The next reduction we'll take a look at is a reduction using LiAlOR3H. Now this molecule is a less reactive version than lithium aluminum hydride. Let's go ahead and take a look at its structure. So just like the lithium aluminum hydride, we have an aluminum atom. Now it's going to have one H attached, and then it's going to have 3 OR groups attached. Typically, the OR groups are tert-butoxy groups, which are very bulky. Now again, it will have a negative charge, stabilized by a lithium atom. So this is a less reactive LAH. It's so much less reactive, it actually will not react with aldehydes. It'll only react with acid chlorides, which are much more reactive functional groups as a whole. So taking a look at this mechanism, we have our acid chloride, we have our modified LAH, we will have the aluminum get rid of the hydrogen as well as its electrons and attack the carbonyl carbon. Now the reason it's going to get rid of the hydrogen and not any of the OR groups or the tert-butoxy groups is because the tert-butoxy groups are too bulky to act as nucleophiles. So they are going to stay put on the aluminum atom. Now we will reform the carbonyl. And at this point, the reaction will stop. So this reagent is an excellent way to turn an acid chloride into an aldehyde without risking further reduction into an alcohol as we normally would with LAH. Now let's take a look at the reactions of acid chlorides with Grignard reagents. So we've seen Grignard reagents react with aldehydes and ketones as in chapter 19. So we'll go ahead and take this acid chloride and treat it with methyl magnesium bromide followed by water. Now for the reaction of our Grignard reagent, remember that we have a bond between the methyl group and the magnesium bromide, and that's going to act as the nucleophile. So the electrons will come up, attack the carbonyl carbon, kicking the electrons up onto oxygen. Now we have formed a new carbon-carbon bond between the methyl group and the carbonyl carbon. Now temporarily, this negative charge can be stabilized by the positively charged magnesium bromide. Now we're going to go and reform the carbonyl, kicking off the chlorine. And at this point, we have formed a ketone. Now we learned in the previous chapter that Grignard reagents also react with ketones. So we're going to have, again, a reaction that keeps going, similar to the LAH. So another Grignard reagent will come in, attack the carbonyl carbon, kicking the electrons up onto oxygen. Now we have 2 methyl groups attached, and we cannot reform the carbonyl because none of these groups are capable of acting as leaving groups. So the molecule will stay in this form until it's treated with our second reagent, which is water. And water will act as a proton source. Ultimately, we started with an acid chloride and we now created a tertiary alcohol. Lastly, we'll take a look at acid chlorides reacting with Gilman reagents. Gilman reagents are similar to Grignard reagents, however, they are not as reactive. A Gilman reagent has the structure of copper bound to lithium. Now the copper atom will be bound to two R groups. This is known as a lithium dialkyl cuprate. And that's another term for Gilman reagents. Now, what makes a Gilman reagent less reactive than a Grignard reagent has to do with the bond between copper and the R group. Now, copper is not as far to the left on the periodic table as magnesium is. That means the difference in electronegativity between copper and carbon is not as great as the difference between the electronegativity between carbon and magnesium. So what we get is we get a less reactive nucleophile for the carbon atom. So the way that we can think of it is that typically the bond between magnesium and carbon, because there is such a large difference in electronegativity, we can really imagine that we have the shared electrons more towards the carbon atom with a negative charge on it. So you have more of an ionic type of bond with a Grignard reagent. So that's going to make this carbon a stronger nucleophile. With carbon and copper, however, it's going to have more of shared electrons. So really, we will have the carbon take on a little bit more of the electrons, but not fully take it on. So we're going to see a slightly negative charge, leaving the copper with the slightly positive charge. Now, because this is not a full negative charge, it's going to make this carbon a much weaker nucleophile. So since it's weaker, it's not going to be as reactive. So let's go ahead and take a look at the mechanism on the next slide. So let's go ahead and react this acid chloride with a Gilman reagent containing methyl groups. Now only one of the methyl groups is going to react, so I'll go ahead and put that one in red. So in our first step, the copper is going to get rid of one of the methyl groups as well as its electrons and attack the carbonyl carbon, kicking the electrons up onto oxygen. So the exact same type of mechanism we've seen in all of the previous reactions. Now, just like a Grignard reagent, we have formed a new carbon-carbon bond. Then we will reform the carbonyl, kicking off the chloride. And we now have a ketone. So a ketone is significantly less reactive than an acid chloride. At this point, a Gilman reagent will not react with a ketone and the reaction stops. So Gilman reagents are just less reactive versions of Grignard reagents, but it's an excellent way to turn an acid chloride into a ketone.